This video reviews some key statistical concepts. Specifically, we cover measures of central tendency, measures of variability, and discuss how we can use measures of central tendency and variability to put numbers in context. That is to say, we will use these measures to understand how one number or score relates to other scores within a larger set of scores. As shown here, we often use symbols to represent these measures, and there are different symbols used depending on if the value is derived from a population or a sample. First, we see the Greek letter mu is used to represent the mean of the population, and the mean of a sample is represented by either X bar or an uppercase M. You will notice these letters are italicized. When we use a traditional letter from the Latin or Roman alphabet, which is what we typically use in English, we will italicize the letter. In contrast, Greek letters like mu are not italicized. We can also see sigma squared is used to represent the population variability, and sigma is used to represent the standard deviation of the population, which we will discuss more later. Measures of central tendency provide information about the average or typical score from a set of scores. The three most commonly discussed measures of central tendency are the mean, the median, and mode. The mean is the most used measure of central tendency in traditional statistics, and we will discuss it more in the next slide. The median is the middle score if you sort or organize the scores from smallest to largest, or vice versa. If we have an odd number of scores, the middle is easy to find, as we can count until we reach the midpoint once the scores are sorted, and there is a single score with an equal number of scores on either side. For example, if we have 5 IQ scores of 90, 95, 100, 105, and 110, we can quickly see the midpoint is 100. If you have an even number of scores, the middle score will be calculated as the average of the two numbers that are on either side of the midpoint. For example, if we had an additional IQ score of 110, the midpoint is now between 100 and 105. In this case, we add the two scores on either side of the midpoint together and divide by 2 to get the median of 102.5. The mode is simply the most commonly occurring score. In the set of data with 6 IQ scores, the mode is 110. If you have 2 or more common scores occurring the same number of times, you can have multiple modes. Finally, if no scores occur more than once, as we saw in the data set with 5 IQ scores, there's not a mode. Returning to the mean, this measure is calculated by adding or summing all of the scores and dividing by the number of scores. The formula for these two actions is noted as sigma x divided by n. Sigma is a Greek letter that we use to represent the function of adding or summing. Thus, sigma x means to add together all the scores on variable x, and we use x as a placeholder for a possible score on a variable. You may also see this formula with a subscript I. This I represents a counter for the individual scores and can be replaced with specific numbers to indicate a specific score. For example, x1 would be the first score on the x variable. The lowercase n here represents the number of scores on the variable of interest, in this case x. In our distribution that we see here, we have 64 scores represented by x1 to x64. Each x is associated with a particular value. For example, if we assume the x variable is IQ, the first person, represented by x1, has an IQ score of 93. The next two lowest scores for x2 and x3 are 94. If we add all of the scores together, we find sigma x, or the sum of the IQ scores, is 6400, and there are 64 scores, so n is 64. The quotient when we divide 6400 by 64 is then 100, which is the average IQ score, or the mean IQ score. As we are working with a sample, we would note this value is the mean with x bar or an uppercase italicized m. We can also see the most frequently occurring score, and the middle score is 100. And in a normal distribution, as represented here, the mean, median, and mode will all be equal, as the scores are symmetrically distributed around the mean, with scores being less frequent as you move above and below the mean. Variability is another important topic in statistics. And even in more advanced statistics, it remains important to understand how values deviate or diverge from some point of interest. In this case, we are interested in how the scores deviate or vary from the mean, which is highlighted. As an example, the deviation for a score of 93 is -7, and the deviation for a score of 94 is -6. We can calculate these deviations for each score in the set, and we will see scores below the mean consistently have a negative value, and scores above the mean consistently have a positive deviation value. Additionally, the deviations are greater in absolute value as we move above and below the mean, with scores right at the mean, that is scores of 100 in this case, having a deviation of 0. When we sum these deviations together, they should add to 0 because the negative and positive values offset each other. Consequently, to create a measure of the total variability in a set of scores, we need to square these deviations. We can then sum these squared deviations to obtain the sum of squares. This value depends on the deviation of scores around the mean, but is also related to the total number of scores, so that as there are more scores, the sum of squares will tend to be greater. To address this tendency, we can average the sum of squared deviations to get the variance. This process is similar to how we calculated the mean, where we summed all the scores and divided by the total number of scores. With the variance, we sum all the squared deviations and we divide by the number of deviations if we're working with a population, or in this case, because we're working with a sample, we will divide by the number of deviations minus 1. If you're curious why we subtract 1 for samples, it's because we know from previous research and testing that samples tend to underrepresent the variability in the overall population. The variance is intended to provide an estimate of the variability in the overall population. Subtracting 1 from the denominator ensures the obtained quotient for the variance is larger than it would be if we divided by n. It also is useful to simply subtract 1 because as the sample size gets larger, the impact of subtracting 1 gets smaller. Ultimately, this reduces the impact on the variance estimate, and that fits our needs because the sample, when it is larger, is also more likely to approximate the population. Thus, when the sample size is larger, less of an adjustment is needed. Now that I'm done chasing my nerdy stats squirrel, we can return to the more basic calculation. In this case, the sum of squares is 672, and there are 64 scores. Thus, the quotient is 10.666 repeating, and we will round it to 4 decimal places. The variance is still in terms of the squared deviations, though, which is not entirely intuitive. We know the average squared deviation around the mean is about 11, but what does that really mean? The standard deviation helps us to move to a more intuitive measure by converting the squared units back into the original units of measure, in this case IQ points. To calculate the standard deviation, we need the variance, and we simply take the square root of the variance to return to the original units. This helps us to know the majority of scores will occur between 97 and 103, and given the scores are normally distributed, we could compute the exact likelihood of a particular score or determine the percentage of scores that will occur within so many standard deviations of the mean. I will not follow that tangent too far, but as an example, in a normal distribution, 95% of scores occur within 1.96 standard deviations above or below the mean. We can use this information to calculate that 95% of the scores in this sample occur between 93.599 and 106.401. We can also use the standard deviation to help us put scores in context. That is to say, this measure of variability allows us to transform scores so we easily know how a score relates to the overall set of scores. This transformed score is called a z-score, which is a type of standardized score. To give you a frame of reference, let's consider how we convert cents to dollars. A long time ago in 2nd or 3rd grade, that conversion was intimidating, probably like this one is now. You had to know there were 100 pennies in a dollar and understand your pennies canceled each other out when you were doing this conversion. Thus, we convert the pennies to dollars by dividing by the number of pennies in a dollar. As adults, we now understand, unfortunately, how these conversions work, so we know exactly how much money we don't have in the bank. The z-score conversion is similar in that we know how many points are in a standard deviation and we can convert into that standardized unit, and that gives us the z-score. For this conversion, we have our deviation. How far is a particular score on x from the mean of x, which is represented here by x bar. Then we divide by the standard deviation. We can convert any particular score on x to a z-score, and we often note the exact score using a subscript. Here we represent that as a lowercase I, and we can substitute any number from the data set x1, x2, x3 to calculate the associated z-scores, z1, z2, z3. As an example, we know the standard deviation and mean for this set of scores, so we want to know the z-score for x1. We simply take the score for x1 of 93 and subtract the mean of 100. Then we divide the difference by the standard deviation and find the z-score is 2.14. This number is potentially more informative than our original scale of measurement, especially if it's a scale we don't understand as well as IQ, because I immediately know the score for x1 is below the mean by noticing the z-score is negative. For all scores below the sample mean, the z-score will in fact be negative. Additionally, the z-score will be larger in absolute value as the score is further from the mean, and the score of negative 2.14 is fairly extreme. If you consider what we learned earlier, you know that this score is particularly uncommon because 95% of the scores fall between 1.96 standard deviations above and below the mean. As we are beyond 1.96 standard deviations, we know that the score is not in that 95%. We should also see the z-score is 0 for all scores equal to the mean, in this case 100, and the z-scores are positive and increasingly large as we move higher above the mean. This z-score distribution then presents us with a standardized normal distribution, and we can easily convert these scores to percentiles. As mentioned earlier, the normal distribution is symmetrical, and the mean, median, and mode are equal. Thus, the shape of the scores is similar to that we see here. And the normal distribution is often referred to as the bell-shaped curve. In this distribution, scores are less and less frequent as you move away from the mean in either direction. When we convert these scores to percentiles, we see a score of 94 falls at about the 3rd percentile. So x1 has an IQ score lower than 97% of the individuals in the sample. The mean falls directly at the 50th percentile, which is the median. And as we move away from the mean, again, the scores are less and less likely, with the 64th score being higher than 97% of the sample. This information provides a foundation for understanding numbers in context, and it helps us see how a particular score compares to the other scores in a set. Additionally, these concepts are a cornerstone of statistics and testing. Thus, occasionally reviewing these concepts is warranted.